Now we want to take the ideas of setting up ice tables, getting to the point of solving the algebra, and doing that work. Enough NaHCO3 decomposes to reach equilibrium. What are the partial pressures of CO2 and H2O at equilibrium? My reaction is 2 NaHCO3 becomes Na2CO3 plus CO2 plus H2O. Kp is equal to 1.39.
All right, so enough NaHCO3 decomposes to reach equilibrium. What are the partial pressures of CO2 and H2O at equilibrium? So we're dealing with some pressures. Makes sense. We got Kp. So we're dealing with gases here. So we want to go ahead and set up our ice table. We want pressures at equilibrium. And so let's see what that looks like. If we're going for amounts at equilibrium, we want to set up our ice table, use the equation as your base, Na2CO3 plus CO2 gas plus H2O gas. And so what we want to do is determine the amounts of the pressures of these two things at equilibrium. And so if we think about the purpose of this ice table, it's to get some algebraic expressions based on variables for those amounts. And so we have this Kp right here. And so if we think about what does Kp look like, right? We know that Kp is equal to, we're going to have it be a ratio of products over reactants. But you'll notice Kp is only pressure. We're only dealing with gases here. Right? Solids don't show up in equilibrium constant expressions, so this is just CO2 times the pressure of H2O. Because those are solids, they don't show up in an equilibrium constant expression in general, and we don't have pressures of gases, or solids even, right? That's not defined, that's why they don't show up here. And so really all we care about are the equilibrium properties of these, and that's all that would define equilibrium. So because these are solids, we actually don't even need to worry about them as far as our ice table is concerned. We know our starting amount is enough NaHCO3, right? There is some of that in here, and there is an amount, but we don't care. It's not going to be changing and showing up in the equilibrium constant expression. So the equilibrium is only going to be based around these pressures. That's what defines the equilibrium. So we start with zeros here. Because they're zeros, we have to shift to this side. The coefficient is 1 in front of there, so we just get plus x. So the equilibrium amount is x and x for each of those. So what I'm going to do is I'm going to take that, I'm going to take those x's and put them into those pressure, so substitute them in there. And so I get that Kp is equal to x times x. Kp is 1.39. That's going to be equal to x squared. So that tells us that x is the square root of 1.39, which is equal to 1.18 atmospheres. So we know that the pressure of CO2 is equal, they're both equal to x, to the pressure of H2O. So that means they are equal to 1.18 atmospheres. So in this case where we have a solid reactant that reacts to become a different solid in some gases, equilibrium is only defined by those pressures of gases. So this reaction will happen until those pressures exist. The relative amounts of the solids do not show up in the equilibrium constant expression. Only the pressures show up. And so that's all that matters. So one of the things, this reaction will happen until you hit those pressures, or conversely, if you put those pressures in, once those pressures are reached, the reaction stops. So the more humid, the more CO2 you fill up your atmosphere, you're gonna stop this reaction.
So NaHCO3 is baking soda. And so what this says is that spontaneously, baking soda does just decompose into sodium carbonate, CO2, and H2O. And these pressures that we get, CO2 and H2O, we know this may seem kind of small that they just become 1.18 atmospheres. But we got to remember that these are partial pressures of just those gases, and ambient pressure is 1 atmosphere. So in order to reach equilibrium, the pressures of those gases would have to be greater than the air pressure that you're under, which just isn't going to happen, which basically just means you're going to drive, if you're in open air, if this reaction starts happening, it's just going to go all the way to completion. In order to reach equilibrium, you'd have to have basically an atmosphere made up of water and CO2, which would not necessarily be livable, and it just isn't going to happen. And so, that if this reaction happens, it's a problem in open air. And so generally there's a big kinetic barrier to this. You'd have to actually get it over that kinetic barrier. But if you heat it up, this reaction really starts to happen. But one of the other things is it can happen slowly, and how you would minimize it is you would make the shift away from products. You should prefer a shift to reactants, and how you can do that is by decreasing the volume, because there's gases on the product side and there's no gas on the reactant side over here. So if you put your baking soda in a sealed container that has, say, a small volume, you won't be able to necessarily produce a ton of gas, and so that'll prevent the decomposition. So if you store it in a sealed container, you would prevent that from happening. Cold temperatures also prevent the reaction from moving to reaching equilibrium. Slow kinetics.
Participation 218, question 3. Enough barium oxide, BaO, is placed into water for the following reaction to reach equilibrium. What is the concentration of barium hydroxide, BaOH2, in the resulting solution? The relevant equilibrium is barium oxide plus liquid water gives barium hydroxide aqueous. Kc is 0.31 for this reaction. This is the third question on participation 218, due Friday, February 18th at 11:55 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, enough barium oxide is placed into water for the following reaction to reach equilibrium. What is the concentration of barium hydroxide in the resulting solution? And then you got the reaction depicted right there. Kc is given as 0.31. Another participation question here. Making our way through. Got, 2 more videos. See you in the next one.